Okay, so this is the third lecture. In the last class we talked about the Archimedes principle, and we showed some slides showing the effect of Archimedes principle on floating bodies. So the principle states that the weight of the volume of water displaced by the floating body is equal to the floating body in the case of a freely floating body. So if you have a body that is freely floating, then if you have a freely floating body, then the principle says that the weight of the volume of water displaced equals the weight of the body. So now the weight of the liquid displaced is called as the volume of the liquid displaced is known as the displacement of the ship, and so what this says is that displacement delta, which is the weight of the volume of water volume of water displaced, is equal to W, the weight of the ship. Then we also know that, or you can say that gamma, which is equal to rho g. So gamma into del equals W. Gamma into del equals W, where del is this. It is the volume of water displaced by the floating body. So that is del. So gamma into del is equal to W, which you can write as gamma into Cb into Lbt equals sigma weight I, where the right hand side sigma Wi represents the net volume, it represents the sum total of the weights. Each of them represents the different weights that are acting on the ship. This will include the dead weight, include the light weight, the hull weight, the dead weight, etc. So that is this. So this represents the total weight of the ship. So this is the weight of the ship, and this represents gamma Cb Lbt. Cb, we have already seen, Cb is the block coefficient. Block coefficient into Lbt gives you del, which is the volume. So this is one first principle that we have to study in order to understand the principles of floating bodies. This is about the forces. Then another thing that exists along with this is the moments. So we have already seen for equilibrium, the forces, the net forces and net moments should be equal to 0. The net force and the net moment should be equal to 0. This is the condition for equilibrium of a floating body. And if we consider the moment, suppose we have initially a body like this. In here you have the weight acting, this is G, the weight acting delta, and this is B. B is the center of buoyancy. This is the centroid of the immersed volume of the liquid. From there upward acts the delta, and this is the weight. So this is weight W of the body, and from below acts up, from the center of buoyancy upward acts the displacement of the ship. Now so as you can see, these two there are two forces. These two forces are these two forces should be equal. W should be equal to delta in the case of a freely floating body. This is the implication that the net forces should be 0 on a ship, on a freely floating body, and the next one is that the net moment should be 0. How will the net moment be 0? Net moments can be 0 only if this weight W and delta, which we are given going up, and W coming down, they act on a same straight line like this. If they are on the same straight line, then you do not have a net moment, then net moment is equal to 0 in that case. So, now suppose that the same body is by some method by for example, by the shifting of weights, G initial has moved from G0 to this new G1 point. The center of buoyancy is here at B. Initially it was in the same straight line, but now G1 which is the new center of gravity has moved to G1, and so here the weight acts W, and here just as before the displacement acts upwards. So, the buoyancy force and the weight W are separated by a distance, by some distance. The buoyancy force and the weight are separated by some distance. Now, if this happens, then there is a net moment acting on the ship. So, there is a weight acting downward here, there is a weight acting upward, means there are two forces and there is a distance between them, it creates a moment. There is a tendency to turn the ship in this fashion, like this. So, there is a tendency to turn the ship like this, in this fashion there is a tendency to turn the ship. So, when this turns, you will have so this is the water line again, and the new, and then G has moved here. Because of this tilting, B has also moved, and as a result of it you will get the new, you will get this delta that is acting upwards and W that is acting downwards, again coming on a same straight line. So, this this is the condition for equilibrium. So, in this inclined position you will see that the moments, the net moment is 0 and the net force is also 0. Okay. Then in the case of naval architecture, in this case, instead of trying to draw all the figures instead of drawing the inclined body, bringing the inclined body into the picture more than once, it is easier to draw the water line itself. For example, instead of the body tilting, if this is the initial state, this is the initial state, and if in the final state, this is the final state. So, this is the initial state and this is a final state, in which case the body has rotated by an amount, some part, more part has been submerged here. So, in this new water line, some more part is submerged on the right side, some more part is submerged on the left side. So, in that case, instead of drawing the body itself again in a inclined position, instead of drawing the body again in that inclined position, it is better if we change the water line to meet this. For example, like this. If I put a water line like this, the meaning of this is that this is the new water line, this much has immersed, a lot of region like this much region has immersed and this much region has emerged. So, this is the new water line, we call the initial water line as WL, then the new water line is W phi L phi. So, you have WL and W phi L phi. This is how you draw the inclined, this is how you treat the inclined water lines in the case of in the case of naval architecture. This is how we do it. So, you will have, initially you have the G here, the B here, then your G has shifted here G1 and this is B1 or B5. We usually write it as B5, or the book on book of Adrian Behrend's book writes it as always B5, where so B0 and B5, B0 and B5. So, and they will be in the same straight line. Now, we already talked about the different conditions of stable, different kinds of equilibrium: stable equilibrium, neutral equilibrium and unstable equilibrium. This is something which we have already discussed. Then, so when you have a suppose the body inclines so the body has inclined with no change in G as such, but the body has inclined due to some other factor. For example, it could be a wind force. A wind force acting on the ship will produce an inclination, a heeling. So, this the body is heeled, this is B0 and this is B5. So, this is the initial vertical, and if I draw a vertical from here, you have to remember this is the water line, this is horizontal. Okay. Even though it looks inclined, even though it looks inclined in this figure, the line is actually horizontal. It is the horizontal water line that is drawn here, and a perpendicular to it is known as it is always the vertical line. So, this is vertical, and where the and where this this line meets the meets this distance, this point we call it as metacenter M. Metacentric height, metacenter M, and of this GM is known as GM is known as the metacentric height. And so, as we showed in the last time, we have K, B, G and M. So, you will have you will see that GM is equal to KB plus BM minus KG, KB plus BM minus KG, and if this is M, the another possibility exists, that is let us suppose the center of gravity has shifted here and this is the new water line. Suppose the vertical meets it here, M G B0 M G. So, this in this case you see that M is below G, and if M is below G, you can see that the moment is again like this. There is no restoring moment. The net moment is the net tendency is to increase the tilting, and this tilting will keep on increasing till the body capsizes. So, that is the this figure. So, what we see is that as long as M is above G, as you see here, as long as M is above G in this figure, the body is stable, and if M goes below G, then the body becomes unstable. Therefore, the condition for stability is that GM should be greater than 0. GM should be greater than 0 is the condition for stability. Okay. Then now we'll have a small we'll recap of something that we already know. It is about the center of mass, or even center of volume. Now we know that the center of gravity of a body is given by, if there are two bodies, m1 plus x2 m2 divided by m1 plus m2. This is the position of the center of gravity of the body xg. Now if we move the distance, if we move the mass m2 a distance d like this horizontally, m2 has been shifted a distance d horizontally, then xg will be x1 m1 plus x2 plus d m2 by m1 plus m2, or the change in the center of gravity is equal to d m2 by m1 plus m2, or it is equal to the change in moment divided by total mass. And if you are talking about a volume, then the change in the center of centroid of that volume will be given by change in the moment of volume divided by the total volume. So this gives you the idea, this is a lemma in center of gravity, a established results that you would all be familiar with. Just to remind, it is the change in moment divided by the total volume will give you the centroid of the volume. That is something that we will be using in many places. Now we have a problem here. Now let us suppose that we have a coordinate system like this, and we have a body. This is z, this is y, and this is x. So suppose there is a body which is of whose surface, and let us suppose this is a body here, this is its water plane W0 L0, and then it tilts and it gets a new water plane area, this is W5 L5. So initially it is here and then it is tilted into W5 L5 about the axis of inclination x. The body has tilted about x. Now we can say directly that the amount of since there is no change in the volume of the body, we can say that the amount of volume that sinks in will be equal to the amount of volume that submerges out. This is true for generally what we call as wall sided bodies. So W5 L5 comes out, W0 L0 goes in, so the volume that comes out is equal to integral, let us say that side is S1 y tan phi, that is because if this is y, z, this is phi and this is y tan phi. Okay, here this is y, so this is y tan phi, this is y, it is a y direction, and if you put this if it is healed by an angle phi, this is y tan phi. So the volume is y tan phi into dx dy. This is the general expression for volume of any body. So in this case you have y tan phi dx dy, and the volume that has come up is equal to, in the this side is S1, this side is S2. So S2 is the volume that has emerged, S1 is the volume that has submerged. So it is the volume that goes in, and S2 is the volume that comes out. S2 is equal to y minus y tan phi dx dy. Now from our formulas, from our definition of the type of body, we have seen that V1 is equal to V2. that is the amount of volume that has emerged is that has submerged is equal to the amount of volume that has emerged. So, V 1 is equal to V 2. Therefore, double integral y tan phi dx dy is equal to minus double integral y tan phi dx dy. Then if you bring this is S1, this is S2, if you bring it to the this to the left hand side, you will get double integral y tan phi dx dy over S1 plus S2 is equal to 0. Now, tan phi is a constant, because phi is a constant, so that does not hold. So, S1 plus S2 in the total surface, let us call it as S, y dx dy is equal to 0. Now, what is y dx dy? Y dx dy represents the centroid of the surface S. Y dx dy, for example, x c will be x dx dy divided by double integral dx dy. So, what we see here is that over the total surface S, y dx dy is equal to 0. It just implies that this is the represents the centroid. So, y c. So, from this what we get is that the what we get is that if there is a, let me read this, let the initial what it says is that if you assume the initial water line to be W0 L0, now after a inclination, the intersection after the inclination along the axis of inclination, if this inclination is very small, then this inclination will be a straight line that passes through the centroid of the body. So, this inclination will be this axis of inclination will pass through the centroid of the water plane area. Centroid of the water plane area in the case of a ship is known as the center of flotation, and therefore, we can say that the body inclines about the center of flotation. So, or the axis of inclination, if you if you assume it to be the longitudinal axis, it will be passing through the centroid of flotation, center of flotation. So, the center of flotation. This makes an assumption that the angle of inclination is very small. So, if you have a small angle of inclination, the body inclines such that the angle of inclination such that that axis of inclination passes through the centroid of the water plane area. This is a very important result, and you should know that always inclination, whether it is heeling or trimming, occurs through the center of flotation or the centroid of the water plane area. That is a important point in naval architecture. Then let us consider something else, that is BM. BM is known as the metacentric radius. Now, let us assume because of the G remains the same, and because of some force acting or some wind acting, there is a small change in the there is a heel and there is an angle of inclination, and the center of buoyancy shifts from B0 to B5, and if that has happened, then the change in coordinate. How do you find the change in coordinate? It is given by the change in volume, change in the moment of volume, divided by the total volume. This I write so this I write so confidently because of the lemma on the masses that I wrote in the previous paper. We saw that the change in coordinate is the change in the moment of volume divided by the total volume. Okay. Then x b, therefore, x b, the change in this is equal to now the volume itself is double integral y tan phi dx dy that we saw in the previous section. Y tan phi is the vertical distance and double integral over the whole surface y tan phi dx dy will give you the volume of the body. So, x if you are trying to get the moment, then x into that y tan phi dx dy divided by double integral y tan phi dx dy, which is equal to del, this is equal to del. So, this becomes double integral x y tan phi dx dy divided by del, and this is equal to I x y tan phi by del, where I x y is the second moment of area, or it is known as the moment of inertia. The second moment is known as the moment of inertia. So, the I x y, since it is x here, it is I x y about the x axis, I x y tan phi dx dy is I x y by del. So, this gives you the expression for x b. Then the expression for y b is the transverse moment is equal to double integral over s again y into y tan phi dx dy divided by del. So, this gives you the shift in the shift in the centroid of the body in the transverse direction because of the healing. Because of the healing, there is a shift in the centroid of the water plane area. That shift is given by y into y tan phi. So, this is equal to double integral over s y square tan phi dx dy by del, that is equal to I by del into tan phi, where double integral of y square dx dy is the second moment of area about the longitudinal axis, this about the x axis, it is I is the moment of inertia about the x axis, and I by del into tan phi. Okay. So, this gives you the this gives you I by del tan phi gives you the shift in the centroid. Then let us consider this. Initially this is your meta center, this is B 0, it has shifted to a new point B 5 and this is y b, this is z b. This is W 0 L 0, W phi L phi. So, what we can see that the distance y b is really this distance, but since we have already said that our angle of inclination phi is 0, we can see that y b is almost approximately equal to the length of the arc B 0 B phi. So, this B 0 B phi is an arc, the length of that arc is almost equal to y b if the angle of inclination phi is very small. So, in that case you get B 0 B phi equals y b is equal to this is the length of the arc. Length of the arc, as you know, is given by r theta. So, B0 m into phi, and here we have that yb is equal to I by del tan phi. Now, if phi is very small, we can write this as I by del phi, okay, I by del, because tan phi approximates to phi in the case phi is very small. So, I by del phi, and so these two are same, and therefore, you get I by del phi equals B0 m phi. So, cancelling out phi, you get B0 m equals I by del. Therefore, the metacentric radius is given by I by del. Metacentric radius is given by I by del. That is a very important formula. That is always that metacentric radius, and so you can see that in a case when, in a special case, for instance, when there is no water plane area, for example, in the case of a submarine which is diving to, which is completely submerged, if the submarine is completely submerged, then you know that I, as you can imagine, there is no I, there is no water plane area. Water plane area, we have already said, is that area where the water line exists, the area at the point of water line. So, if there is no water plane area, then there is no I, and then therefore, B m is equal to 0, or B and m coincide in a case of a submarine in a submerged condition. So, such different kinds of ideas you can get. Then it is probably wise to remember the center of remember the moments of inertia of various bodies, various types of water plane areas. For instance, if you have a rectangular water plane area, and suppose that we are taking this is L, this length is L and this length is breadth, then if you are taking moment about this, then the moment of inertia of this system is given by L b cubed by 12 about this longitudinal axis. So, about this longitudinal axis, the length of the the moment of inertia is given by L b cubed by 12, L b cubed by 12, and in case you are taking the moment of inertia about this axis, then moment of inertia is given by B L cubed by 12. Moment of inertia about a transverse axis is B L cubed by 12. So, and similarly, if you have a circle, the moment of inertia of this kind of area is equal to r power 4 by 64. Sorry, d power 4 by 64. D power 4 by 64. This gives you the it gives you the moment of inertia of a circle about an axis that is passing through its center. So, if any axis passing through the center considered, you will get the you will get the moment of inertia as d power 4 by 64. So, these are some important formulas, and now let us do some problems regarding this that comes in this chapter. For instance, suppose there is a boy. The problem is as follows: there is a boy and this boy is of radius something. Let us say it is of mass m. It has mass m, and it is a hollow sphere. So, there is an inside volume and an outside sphere and a small amount of material of some thickness, and then inside radius, that is a smaller radius. So, it is a steel plate of 3 mm radius, 3 mm 3 mm thickness. So, the thickness of the steel plate is 3 mm and the body itself has a mass capital M, and the buoy. Now, you are asked what, and let us suppose that the density of the material of the buoy is rho s, density is rho s, and your question is under what condition will the body float. So, the problem is you have a buoy which is actually a hollow spherical hollow shell. So, there is an outside volume and an inside there is an outside surface, there is an inside surface. The thickness of the plate is 3 millimeter, and the rest of it is hollow, and this is placed on water, and under what conditions will the body float? That is your question. Now, first of all, we bring in the Archimedes principle. So, when you have the Archimedes principle, you say that gamma del is equal to W. This is the first principle where or rho of water into, this is not the rho of the steel plate, this is the density of water into del equals the mass of the body m in this case. So, we have removed the acceleration due to gravity, the g term has been removed, and therefore, you get the formula that rho w into del is equal to m. So, m is the mass of the floating body. So, this is the first rule. Then the del of the body, let us assume that the volume of the submerged sphere, this is equal to 4 by 3 pi d cubed, 4 by 3 pi d 0 cubed. This is the volume of the submerged half sphere, half of it. So, it is floating like this in the with the center that has to be mentioned. The body is floating with the center here, center at the water line. So, half of it is inside, half of it is outside. The volume submerged is given by 4 by 3 pi d 0 cubed into half. Half of this is the volume of the submerged half sphere. Volume of the submerged half sphere, del is equal to half 4 by 3 pi d 0 cubed. Then the mass of the spherical shell, is given by m of steel is equal to rho s into 4 by 3 pi. Remember, this is a hollow sphere, it has an inside and an outside, and the mass comes only from the steel. So, the mass does not come from the hollow part inside, that does not add to the mass. So, when you are finding the mass of the body, you need to take only the steel weight. So, steel volume into consideration. So, 4 by 3 pi into d 0 cubed minus d 0 minus 0.003 cubed. So, mass, now putting this formula rho w into del is equal to m, you get rho w into half into 4 by 3 pi d 0 cubed is equal to rho s into 4 by 3 pi into d 0 cubed minus d 0 minus 0.03 cubed plus so this gives you the this gives you the formula, and from this you will get when you do this you will get a cubic equation. You get a cubic equation, and that will that when you solve that, you will get the value of d0. So, that will give you the condition that is required for the that will give you the condition that is required for the body to float in this fashion, as we have just said. Then there is the second problem. Another problem states that there is a cone floating upside down in water, and this is a spherical cone. It's this is a circle, it is a cone, and so this has a draft T and it has a depth h. So, it has a draft T and a depth h. Okay. So, you are told these things, this is T, there is h, and this distance, this radius is diameter is d, capital D, this diameter is small d. So, small d and capital D. So, these two are given, and then you are told also about the cone's material, its specific gravity is gamma c for the cone, and gamma for the specific gravity is density into g. So, specific gravity of the cone is given as gamma c, specific gravity of the water is given as gamma w. So, gamma c and gamma w, and now the question is, under what condition will the cone float in this fashion? So, for this kind of problems, we need to have there are two conditions. The first of it is the condition that Archimedes principle, the volume of water displaced is equal to the volume of the weight of the volume of water displaced is equal to the weight of the body itself. That is number one principle. The second principle which we saw today is that Gm should be greater than 0. So, if both these conditions are satisfied, then the body will float upright in as we have said in this problem. Then the first Archimedes principle says the Archimedes principle says that gamma c into volume of the cone below this is equal to gamma pi. This is the weight of the cone itself, which is equal to the specific gravity of the cone into the total volume of the cone. So, pi d square by 4 h. So, into 1 by 3. The volume of a cone is equal to 1 by 3 pi r square h, 1 by 3 into pi d square by 4 into h. This is the volume of any cone. So, these are some common geometric terms that should be familiar with, that is the volume of a cone, volume of a parallelepiped, or a volume of a rectangular barge, volume of a sphere. Similarly, the moment of inertia of a couple of things like moment of inertia of a spherical surface, moment of inertia of a rectangular surface, moment of inertia of square, and parallelogram. These kind of things it is better to remember when you are studying this section. So, Archimedes principle says that the mass of the cone, that is gamma c into 1 by 3 pi d square by 4 h, the mass of the cone is equal to the weight of water displaced, R w into pi. This much volume of water has been displaced, pi d square by 4 1 by 3 again 1 by 3 pi d square by 4 into h into t, in this case t. This is the height of the cone is t. So, the volume of water displaced is this, it is 1 by 3 pi d square by 4 t, this is the volume of water displaced, into gamma w will give you the weight of the water displaced. So, the weight of the water displaced is equal to the weight of the cone here. So, this just represents the weight of the cone, which is equal to specific gravity of the cone into the volume of the whole cone. So, just to specify this, just to stress on this again, the volume of there are two volumes here. One is the volume of the whole cone, and the other is the volume of the area submerged. So, when you are doing the mass of the cone, you take the whole volume, the whole volume of the cone, and when you take the weight of liquid displaced, you take only the volume that is submerged. So, this gives you gamma W into, this is the first principle. Then we can put a kind of geometrical similarity, because it is the same cone. Geometrical similarity says that d by d is equal to t by h. D by d is equal to t by, this is d, this is not d, sorry, this is h. I wrote wrongly, this is h. So, d by d is equal, this is d, this is small d, and this is h. So, d by d is equal to t by h is a geometrical similarity, and let us say that alpha is equal to gamma c by gamma w power 1 by 3. So, gamma of the cone by gamma of water, we will write it as power 1 by 3, we will write it as alpha. So, we obtain T is equal to, therefore, alpha h from the previous principle. Then now we need to get GM. Okay. GM is our final goal, and we need to say that GM of this system will be greater than 0. That will imply stability. GM is greater than 0 will imply stability. So, to get GM, we need to get KB plus BM minus KG. This is the way to get GM. This is the only way to get GM. KB plus BM minus KG will give you the GM. The metacentric height will be given by KB plus BM minus KG. Now, so we need to find for this cone what is KB, what is BM, what is KG. We have formulas for everything. For instance, KB is the centroid of the, if you look at this, KB is the centroid of the KB is the centroid of this region of the cone. The cone inside this, it is given by KB. So, KB is equal to 2 by 3 of T. This is another thing. The centroid is centroid of a triangle. If you have a right angled triangle, the centroid of this triangle is at 2 by 3 from here, 2 by 3 from this side, or 1 by 3 from this side of the total height h. So, 1 by 3 h, 2 by 3 h. So, KB is equal to 2 by 3 T, and KG is equal to 2 by 3 h. So, Kg is the Kg for the whole cone. Remember, we are talking about the center of gravity of the whole cone. So, that will be at 2 by 3 from the 2 by 3 of the h, 2 by 3 of this whole distance. The distance from here will be 2 by 3, distance from here is 1 by 3. So, okay. So, 2 by 3 h Kg is equal to 2 by 3 h, and Bm we have seen is equal to I by del I is equal to pi d power 4 by 64, and therefore, Bm is equal to pi d power 4 by 64 divided by del. where del is equal to 1 by 3 pi d square by 4 into T. This is the underwater volume. I do not have to repeat it. So, this is the underwater volume divided by del. When you do that there, you will get Bm for the whole thing. So, once you have your all those things, you can get Gm. You do is Kb plus Bm minus Kg, and just putting all these things together, we give the condition that Gm should be greater than 0. This is the condition for stability. So, Gm is greater than 0, and when this condition is met, then you have the case of a cone exactly sitting in an upright condition like this. So, this is the problem. We will work on similar problems in the next class, and so we will stop here today. Thank you.